video is part of the lecture for multivariable calculus, and I'm gonna solve one example that shows how to use Riemann sums to calculate the double integral, or basically finding the volume of a solid that is above the region 0, 2 cross 0, 2, which means that it's a square on the xy plane, and it's below the paraboloid z equals to 16 minus x squared minus y squared. So let me start. Something that I always recommend is to graph the region that you have. So let me have the x, y, and then z axis, and I'm gonna graph this paraboloid first. It's 16 minus x squared minus y squared. If x is equal to 0, then z would be equal to 16 minus y squared. So it is 16. Now I have like a parabola like this upside down. When y is equal to 0, z would be 16 minus x squared. So on the xz plane, I also have a parabola that is upside down like this. So if you want to see what happens when z is equal to 0, then we get 16 equals to x squared plus y squared, which is a circle of radius 4. So that's why we have an upside down parabola like this, paraboloid like that. And then we have the region R. So let me graph the region R. So it's x is between 0 and 2, y is between 0 and 2. So I have this is square in here, and now I want to find the volume that is below z equals to x squared minus y squared, which is below this paraboloid, and it's above this region. That's why if I want to graph kind of roughly that what we have, this is my parabola, and it's the paraboloid. It goes up to 4, and basically I have something like this region. You see, it doesn't fill out the whole space on the x, y in the first octant, so we just have just part of it that goes up to the top of the paraboloid. Let me give you basically the idea. So you see, this is z equals to x squared minus y squared. Let me make it full. Z equals to 16 minus x squared minus y squared. Now the region would be this region. Okay, so I have a square on the xy plane, and now you see, just pay attention to the shape, and then you will see that we just want just part of the paraboloid that is above this square. I hope you can kind of feel the shape. Okay, so now let me graph R as well. So this is x-axis. Let me bring it a little down. Then I have y-axis. This is x-axis, y-axis, and then it's from 0 to 2, and then 0 to 2. Okay, 2, 2. This is 1. This is also 1. And it says that with m and n equals to 2, so basically we want to just divide the interval from 0 to 2 by 2, just because m is equal to 2 and then n is equal to 2. So we have like these 4 squares. Okay, now if I want to find this volume, okay, not using the double integral, just using the Riemann sum, we have some options. I'm gonna use the middle point of each of the square. What do I mean? I have the squares. Just assume that this xy plane, I have these squares, and in each of the squares I can use the middle point, and then I find the volume of the middle point, this is square, this is small square, the volume of this box, and the height of the box would be the value of the function at the middle point times the area of the base. The area of the base is what? So the area for each one of them would be the same. For example, for this one would be delta x times delta y. And then what is delta x? Delta x, it's obvious in here that is 1, but it would be 2 minus 0, the interval on the x-axis, divided by n equals to 2, times delta y is the interval on the y-axis, which is 2 minus 0, divided by m. M is also 2. So you see that's 1 by 1, the area is 1. The area of each one of them is 1, so the volume is kind of approximately the sum, okay, for all the sample points that we get, okay, the value of the function at the sample points, which would give us the height, times the area of the base. Okay, so this is I from 0 to 2, j from 0 to 2, and for all this notation I recommend that you go back and watch the video of definition of the double integral, so I explain all the definitions on there. So we need to find the sample points, so I'm gonna choose the middle point to be my sample point first. So the middle points are where? Like here, 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 here. Now, what is the coordinate of the first middle point? It's 1/2, 1/2. So I'm gonna say that the volume is f of 1/2, 1/2, the coordinate of the first middle point times delta A, plus the second middle point is here, it's 3.2 and 1/2, the coordinates of that, 3.2 and 1/2 times delta A. The next one is this one in here, which would be f of 1/2 and 3/2, and then times the area of the base. And the last one, which would be here, would be the coordinates of the point, and then I need to find the value of the function at that point to give me the height. So let me do, for example, for this one, this is 16 minus 1/2 square minus 1/2 square, and then delta A, we calculate that is also 1, and I'm gonna add it to, for example, for this one, this is 16 minus 3/2 square minus 1/2 square, because this is basically the formula for the function in here, times delta A. Delta A is also 1, and then if you calculate the whole thing, we get 54. Do some algebra, find them, and then add them up. We get 54 for all of them. Okay. We can also use the as the sample point, we can also use the lower left corner point. Where are they? For example, on this square in here, I'm gonna choose this one. Okay, and then I'm gonna say that the volume is f of the coordinates of the point is 0, 0 times delta A, plus, for example, for this square in here, the lower left corner would be this point. The coordinates of that is 1 and 0, and then times delta A, plus for this one, I'm gonna choose this, which is f of 0, 1 delta A, plus for this square in here, I'm gonna choose this point as the sample point, and I'm gonna get f of 1 1 delta a. Similar as before, we're gonna plug in into my function to find the values. Delta a is still 1. Okay, and then you can plug it in there for all of them, plug in the points, the sample points into there, and then we get 60 as our a volume approximation of the volume. The other point that we can get is the upper right corner. Upper right corner point, which is which one? The upper right corner would be this one. For example, for this square in here, I'm gonna get the upper right corner. Okay, and I'm gonna say that the volume is approximately f of the coordinates of the point is 1 1 delta a plus. For this square in here, I'm gonna get this point, which is what? F of 2 and 1 2 and 1 delta a. For this square in here, I'm gonna get this point. Oops. I'm gonna get this point in here, which would be what? Which would be f of 1 and 2 delta a plus, for the last square in here, the sample point that I choose would be the upper right corner, which would be f of 2 delta a. Similar as before, just plug in the points into the function to find the actual value, and then times delta a, which is equal to 1, and then we're gonna add them all up. If you do all the calculations in here, you're gonna get 44. Now I have a question. The question is, which one is the best approximation? Is the best approximation? To actually say that which one is the best approximation, we need to find the actual volume. The actual volume using the double integral would be the double integral of the function 16 minus x squared minus y squared dA over the region R that is given, okay? And it would be from 0 to 2, 0 to 2. If you do all this calculation in here, which we're gonna explain on the other videos, it would be 16 over 3, which would be 53.33. okay, so as you see, it's very close to the actually middle point. So the middle point approximation. So the middle point approximation gave us the better approximation to find the volume.